Good afternoon and welcome to the second week of quantum computing. So we'll start with a quick revision of what we discussed last week, and then we'll continue with the course. So last week we discussed how we can actually speed up an algorithm, and achieving a better complexity is one of many options. And that's what we're actually aiming to do in quantum computing, that we want to solve certain computational problems much faster than classical computers uh, could do by using quantum parallelism, which can lead to improved complexity classes. Very importantly, this does not work for every possible problem. It works for certain problems, and it's quite challenging to make all of this happening. And we'll be exploring these challenges in this course and see how we can build such algorithms. Uh, we then looked into one example, which was the black box search, and we saw that with a traditional computer, this is O of n, and with a quantum computer, we can use the so-called Grover algorithm, something we will see in a few weeks, in which we can get a squared speed up by solving this problem in O of square root of n. We've looked at one possible architecture, the one that D-Wave offers. We'll be exploring more architectures in this course. We talked about the prerequisites of this course and the organization of the course and the schedule. So after we had discussed that, we also looked into some of the references this course is based on. In particular, most of this course is based on quantum computing for computer scientists. These other books are excellent references as well if you want to study quantum computing further. And then we also briefly looked into two further readings, two chapters that you should have read. One is Quantum Technologies that Daniel Achanin, one of the CTOs of Microsoft, published in one of my books a few years ago, as well as a more recent, very recent book chapter I published earlier this year. Who of you actually read these two book chapters to some extent? Maybe you can signal this here in the chat. If you have done that, that would turn out to be a very helpful foundation for the coming months. And we'll be exploring all of this in greater detail. We've also talked a bit about fears around quantum computing, which I think are, if you read this article here that appeared in Foreign Policy a few years ago, I really wonder if these authors actually have studied quantum computing in order to make such claims. And we saw there are some impacts on encryption, and there are now new standards. These standards could be also something maybe that is interesting towards your seminar presentations in case you start looking for topics already. And I told you in the coming weeks, we want to make our way to quantum theory and then look into architectures, how we can use quantum theory or quantum mechanics to do computing. So the computing part will start in chapter 5 and will take us a little bit to make it there. And we want to explore quantum theory. For this, we need to see different kinds of systems, including quantum systems. And in order to describe all of this, we will need plenty of mathematics. And the mathematics, the foundations, that's the focus on what we're doing today. We will look into complex numbers. Who have you studied complex numbers before? I guess most of you have. Those who have done, or those of you who have studied engineering or computer science, all of you should have seen complex numbers. But we also have some business students every year or exchange students. So if you have done complex numbers or studied them to some extent, maybe send a green reaction. If you're not familiar with complex numbers, maybe send a different reaction, like a red one, for example. And there are every year some students who haven't come much across them. And what I will do now is I largely provide you with quick overview of complex numbers, and those of you who have seen complex numbers before, for them this will be a revision, but there will also be some new stuff that probably most of you have not seen when it comes to complex numbers. And then after that, we will look into vector spaces, so vectors, matrices, and structures of that sort. We will revise which operations we can use in vector spaces, but then we will not just use vector spaces on real numbers, but actually on complex numbers. So we will plug our complex numbers into those vector spaces, and then some stuff will work like before, but there will be some new topics as well. So for some of you today, maybe lots of new stuff. For some of you, maybe more like a revision, but I think for every one of you, there will be quite some new stuff, especially around complex vector spaces and some selected topics around complex numbers. So why are complex numbers so important to this course? Because complex numbers, they're the very foundation of quantum mechanics, because in quantum mechanics, we want to use, or we want to see quantum mechanics as a generalization of probability theory. And it turns out this can be done very well with complex numbers. And these phenomena around quantum mechanics, they can be described very well with complex numbers. And that's something we are not able to describe with real numbers. With real numbers, we could describe, for example, probabilistic systems, and quantum mechanics is another step because it's a generalization of all of that. And for that, we will need those complex numbers. So it's very important we study them and revise them now. And where do these complex numbers fall into? Say if we have an equation, something like x squared plus 1 is 0, we could wonder, how can we solve this? And with the sets of numbers you have seen so far, without complex numbers, you are unable to solve this, because whatever you plug in here, be it a positive number, a natural number, or some integer or a real number, this one here, when you take x and you square x, and since x is either positive or negative or 0, but you square it, then x squared is 0 or greater than 0. And then if you add 1 on top, you're unable to get to 0. So we are unable to solve this here. And one of you turned on the camera. You maybe recorded and you could appear in YouTube. So you're obviously welcome to keep your camera on, but you may be appearing in the recording to some extent. So, and you don't need to turn on your camera to follow the lecture. So, so we can look quickly at these sets. So the positive numbers are numbers 1, 2, 3, and so forth. The natural numbers, we take the positive numbers and extend them with a 0. So it's 0, 1, 2, 3. Integers, or so-called whole numbers, they are the positive numbers, but also the negative ones of the positive numbers. So it's also -1, -2, -3. We can further extend that set by looking into the rational numbers. And those are fractions where we divide m by n, where m is an integer and n is a positive number. So we don't divide by 0. And then the real numbers are yet another extension of that set, because we take these rational numbers, which include the positive numbers, the natural numbers, and the integers, by the way, and we extend that with other numbers, like like a square root of 2. We could have, but also, for example, e or pi, e divided by pi, and these numbers, we cannot express them as rational numbers. So this is yet another set which extends our rational numbers. But even these real numbers here, they don't help us to solve x squared plus 1 is 0. And for that, we need to introduce a new mechanism. And we could also just rephrase this and say x squared plus 1 is 0, which is just the equivalent to x squared is -1. And with the real numbers, we are unable to solve this because all the real numbers we can plug in here and we square them. The square of a real number is 0 or greater than 0, but not negative. So we actually need a different mechanism. And for this, we introduce a number I, which is the imaginary number. And when we take I and we square it, I squared is -1. Or we can say I is the square root of -1. And this is now a key part of the so-called complex numbers that we will introduce very soon. And for that, I will switch very quickly to my whiteboard and we can try to do some calculations with I and then introduce the so-called complex numbers. So, what we've seen is we can say I, so I is the square root of -1. So I squared is -1. And with that, we can try to do some calculations. Like I want to know from you, what is I cubed or I raised to the power of 3? And if you have an idea what that could be, you'll see the solutions in the slides for some of these problems. It's helpful if you don't just copy paste this from the slides. But if you have an idea what I cubed could be, so I times I times I, then let us know in the chat what you think a solution for this could be. And we got a few suggestions. Almost all of them say it's -I, and that's correct because we can say this is I times I, which is -1, and then -1 times I is -I. We can also look into other examples. We can say 1 divided by I, and I want to simplify this. It turns out this is simpler than it looks like because I can take 1 divided by I and I can extend the numerator and the denominator with I. So I put an I here and an I there. And then this is I divided by -1. Since I have this I times I, we've seen before, is -1. Then I divided by -1 is just -I. If you see i's in the denominator, oftentimes this doesn't look that great. So rather try moving the I to the numerator and don't have i's in the denominator if possible. It just looks much better. And with that, we come now to the complex numbers. And complex numbers, for example, we call one Z, and Z is an addition of A and the product B times I. And A and B are real numbers. And what we sometimes say is that A is the real part of Z, real part, and B is sometimes called the imaginary part. So our number Z has two components, A and B, but B is multiplied by I, the imaginary number we have just started to look into. Sometimes these complex numbers, they are also, for example, just written AB as a tuple, as one example. And there are a couple of other ways how you can sometimes write them down in short, but for now, we'll typically just write Z is A plus B times I. And I want to know from you, where have you come across applications of complex numbers so far? I know when you study, for example, computer science, you may learn about complex numbers in mathematics 1 or 2, but I'd like to see if you have come across any applications. So you can just share them because we also have students from other degree programs, not just from computer science. Some students, they say from electrical engineering, yes. Some like the Fourier transform or the fast Fourier transform. Some have seen them in control systems. And all of that is correct. And something I personally feel often is when you study computer science, you learn about complex numbers, but you don't really see applications. So I don't know if you learn complex numbers and you take a programming 1, programming 2 class and you learn about object orientation. You're often tasked with writing a class to represent complex numbers, but you don't really know what they're useful for. One student has seen them in global positioning, okay. And there are various applications. So in physics, in electrical engineering, a few years ago, some students told me from civil engineering that they needed complex numbers for some of their calculations. It turns out you can use complex numbers to describe some computer graphic problems. And there is even an extension of complex numbers, which is even more useful for that. But most computer science students don't really see applications of complex numbers throughout their studies. And it turns out there are, and this course is actually about one, which is quantum computing. And just for the revision and just to make sure everyone is on the same page, we will now look at a few fundamental operations of complex numbers just to show that we are all on the same page. For example, we can add complex numbers. So we can say we have, for example, we'll do additions and we say addition, and we'll see one example. So we can have, say, our complex number Z1, which is 5 minus 2i, and Z2 is 1 plus 3i. And I want you to add them, so Z1 plus Z2. If you have a solution for what the addition could be, please share this in the chat. What you need to do is you need to add up the real and the imaginary parts, and then you have a new complex number. And the solution is, so it's 5 plus 1, which is 6, and then it's minus 2i plus 3i, so 6 plus I. That's correct. We can also think, you can also subtract complex numbers, obviously. You can also multiply complex numbers if you wish. We can think about an example very briefly for adding for multiplying complex numbers. So we can say we have our so multiplication. We have Z1, which is 3 minus 2i, and Z2 is 1 plus 2i, and you are now tasked with multiplying them, so Z1 times Z2. If you have, you can think about how you would multiply them, but eventually this is just algebra because you have these two numbers with their components, and so we can write this out. So it's 3 minus 2i times 1 plus 2i. And I want you to think about what the solution could be. and then we can compare this here. And I'll wait for your suggestions in the chat what the product of these two complex numbers could be. We get multiple answers, but a majority for one. So what we see is it's 3 times 1. This is the first one. Then we have plus 3 times 2i. Then we have the next component, which is the minus 2i times 1. So minus 2i times 1. And the last one is the minus 2i times, so minus 2i times 2i. And so this is minus 2i times 2i. We can try to solve this now. So this is 3. This is 6i plus 6i minus 2i. And then what we have here is we have a 2 times 2, which is 4. So minus 4i squared. Minus 4i squared. And this one we can simplify further. So it's 6i minus 2i, so 3 plus 4i. And minus 4i squared is, remember, the I squared is minus 1 times minus, so it's actually plus 4. And then we have 7 plus 4i. And this is something that most of you wrote, so it's actually one complex number, and most of the answers in the chat were correct. So you should simplify this as far as possible, and when you have things like this, like I squared, the I squared will turn into minus 1 with minus here, so plus 4. So do you all feel okay with multiplying complex numbers? Maybe just let us know with a thumbs up or thumbs down if this is something you feel okay with. But I see only positive responses. I think for some of you, it's probably a good revision since it may have been a few years since you did your Maths 1, Maths 2, and then especially the computer science students may have not needed these complex numbers any longer. And so I think it's important we do this revision. Now, we can have complex numbers, and we can also try to represent them or interpret them from a geometric representation. And if we can, let's maybe look at an example. So geometric representation. So we have two axes. We have the real part as well as the imaginary part. And now if we have a complex number like z is 3 plus 4i, we can try to plot this in here in this so-called complex plane. So geometric representation, complex plane. So we have the 3 here for the real part, and we have a 4 in the imaginary one, and then we would have this something like this. That would be, even for the ticks now, don't look perfectly the same on the two axes, but we could represent 3 plus 4i as a vector, so to speak, as a geometric representation. And this brings us to yet another concept for which we need or which we call the modulus or absolute value of the complex number. You could also see this as the length of the vector. And in order to calculate this modulus, so we have a complex number z, and we want to know its modulus or absolute value, this would be so we say this is a plus b times I, and for that we take the square root of a squared plus b squared, and very importantly, the result that we want to get out is the positive one, so just to highlight this. And now I want to know from you, we have our z up here. What would be the modulus of a z where z is 3 plus 4i? You can think about this and share it with us in the chat. So we have 3 squared plus 4 squared, and then we take the square root of that. So it's 9 plus 16, the square root of that. The square root of 25 is 5. So that's the modulus or the absolute value of the complex number, or if you see it as a vector, it's just the length of the vector. So that's why the geometric perspective actually helps a lot. And then there is one other fundamental concept, which is the conjugate of a complex number. So we call this the conjugate. And there are various representations to write this down. One way could be something like this. We have z, and we put a bar on top, and the conjugate of this would be, so we have a plus bi, and I want the conjugate of that. What we do is we just flip the sign of the imaginary part. So this would be a minus bi. We just change the sign of this imaginary part. And there are some other notations. Sometimes this is written as a z star, for example, or we have this z bar on top of here. These are two notations that are quite common, and we can look at one example. So we can say z is 5 minus 3i. I want to know from you what's the conjugate of this. And if you know the answer, send it to the chat, which is straightforward. So it's 5 plus 3i. We will switch back to the slides for a moment. So here in the slides, we've skipped one slide, which are but I've shown you this on a whiteboard that the complex number is a plus b times I. We've written this down. We've looked into applications. We've seen some from physics, from electrical engineering. Computer graphics can be interpreted in some cases through complex numbers, but there's also a generalization of complex numbers for this, or an extension. In quantum computing, what this course is about, we will actually deal with complex numbers all the time now. And we've seen so far the addition, multiplication, modulus, or the absolute value, and the conjugate. We've seen also the geometric representation in the complex plane, which I had visualized for you. And from that geometric representation, it turns out there are more representations of complex numbers, which are the polar representation and the Euler's formula. Who of you remembers this? I just want to do a quick double check and see who of you remembers the polar representation or the Euler's formula. If you remember, maybe some positive reaction. If you don't remember that, send some negative reaction. And I have this here for you. So what we have here is the geometric representation, something we've just seen before, that we have on the one axis the real part, on the other axis the imaginary part, and we have our complex number AB. And we have, what we can see here in this visualization is we have a variable r, which is just our modulus we have seen, or the absolute value, or the length of this vector. But this vector also has an angle with our axis for the real part, and this angle is often denoted theta. In basic geometry, you learn how to calculate this angle. So I'm not discussing examples here with you because this is just fundamental geometry. If you need to look it up, take a look, for example, in the book Quantum Computing for Computer Scientists, how to calculate these angles. But what we can see is we can describe a complex number in two different representations. For example, with the polar representation. So our complex number, which is z, which is a plus b times I, we can represent this in polar representation, which is some format you have seen probably not only for complex numbers, but also in some other cases like polar representation. And what you can say then is our a can be expressed as r times the cosine of theta, because we have our angle theta here between the vector and the axis for the real part. So this is the cosine times theta, and we need to multiply this with the length of the vector. Like this, we can express a. And b can be expressed as r times the sine of theta. And that's our b, but we always say b is multiplied by I, so I still need to put that I here. And now we see that this component, as well as the next component, they both have this factor r, which is the length of this vector. We can just move this out r and say r times, and then in parentheses, our cosine theta plus I times sine of theta. So I just moved the I to here in the product, but that doesn't make a difference. And now this is the so-called polar representation. And this polar representation can be expressed or can be changed to the Euler's formula. And the Euler's formula looks something like this. The Euler's formula is r for our length of the vector times e to the power of I times pi. And I times pi refers to the complex part, and the theta here is just the angle of how far you need to move from the real axis to the left to get to the complex number. So this is the Euler's formula, which is just another representation for the complex number. And with the Euler's formula, you can do certain computations around complex numbers more efficiently. Sometimes this is also helpful if, for example, you want to get the square root, or you want to get the root of a complex number. That's something you may also learn when you study complex numbers. But if you're not familiar with this Euler's formula, please go back to your Maths 1, Maths 2, where you learned it, where you should have learned it, or you can look up the details in our book. or in our course book, the Quantum Computing for Computer Scientists. And it turns out with this Euler's formula or dipolar representation, we can do some quite interesting calculations that I want to show you in a moment. And for this, I'll switch back to my whiteboard. Well, what I showed you, you'll find it in the slides. But before we use this, I have another quick example around complex numbers, just that we get a little bit more practice with complex numbers. And I want you to simplify a complex number, 1 plus I divided by 1 minus I. Does any one of you have an idea how, without looking into the slides, of how we could simplify such a complex number or this division of two complex numbers? One student says is multiply all by the conjugate, and that's correct. And we will see that this can actually be simplified very well. So we have our 1 plus I divided by 1 minus I. And we can say, well, this is our 1 plus I divided by 1 minus I. And we multiply this with the conjugate of the denominator. So this is 1 plus I times 1 plus I. So what you see, this is here the conjugate of the denominator. And now we just want to multiply these complex numbers. So we multiply the numerator and the denominator. And maybe you can start with the numerator. And if you have a solution, what this product here in blue would be, you can share it with us in the chat. I'll wait for you and see when we get the first answer about what the product would be. So got already the right solution. We'll do it step by step so we're all on the same page. So it's it's 1 times 1, which is 1. Then 1 times I. Then I times 1, which is another I. And we have the I times I. So plus I squared. We'll simplify this in a moment. Do you also have a solution for the product of, or for the result of the denominator? So we multiply 1 minus I with 1 plus I. If you have a suggestion for that, just let us know. So in fact, what we are doing here for the denominator, so it's a minus b times a plus b. Remember that, and then this is just a squared minus b squared. So what we get here is we can see this is, if a is 1, so it's 1 squared, which is 1, and b is I, so minus I squared. And now we can try to simplify this. So we have our 1, then I plus I, so plus 2I. We have our I squared, which is minus 1. And down here we have our 1 minus I squared. So I squared is -1 minus that is +1. So we can see that finally this -1 and this one disappear. So it's 2i divided by 2, which is just I. So it turns out that this one here could be severely simplified. Do you all feel okay with this division? Maybe just let us know with thumbs up, thumbs down, if this looks reasonable to you. And now we will do something that many of you will probably have not seen before. We'll do another example. We will do something. We want to calculate what is I to the power of I. Did anyone ever see any one of you ever see something like this before you looked into this course? Maybe when you studied complex numbers in your first year, have you ever seen something like I to the power of I? If you've seen this, send. I only see negative reactions. Maybe send more. And if anyone has really seen this, send a positive reaction. I have to tell you, I also didn't come across that kind of stuff when I was an undergrad student. I had never seen anything like that. I only started coming across this a few years ago on the internet. And there are excellent YouTube videos about this stuff. So when I have some free time, when I don't know, I sit in a hotel or I'm in bed in the evening, I sometimes watch some YouTube videos, and there are very interesting math videos from a guy that calls his channel Black Pen, Red Pen, or something like this. Does any one of you know this guy? He's a Chinese guy in the US and shows some very weird calculations on a whiteboard. So I sometimes watch this when I'm in a hotel and I have nothing else to do in the evening. And there's another guy, I forgot his name, but I think he's an Iranian guy somewhere in Europe or US, and he also does excellent videos about some strange complex number stuff. And then this is something I would have never thought about, I to the power of I, but it turns out this can be solved. And for this, we will need a quick excursus. So before we come to I to the power of I, we need something else. So we leave some space here. We'll come back to that. We'll do an excursus. We want to know about the logarithm of a complex number. Did any one of you see this before in your undergrad, the logarithm of a complex number? Again, send us a positive or negative reaction. So one has seen this. Okay. But if you have not seen that, that's fine, because this is probably not part of your typical introduction to complex numbers. And that's why I promised you, for most of you, there would be something new. And someone wrote here, two students wrote in the chat about a YouTube channel, 3 Blue, 1 Brown, if this is similar. So I don't know this name, but feel free to look it up. Maybe I've seen those videos as well, but I'm not too familiar with all the names of these YouTube channels. So we saw before that when we have our complex number, we can represent it with Euler's formula. And we said this is r for the distance times e to the power of I times theta, which is this Euler's formula. Now how can I apply the logarithm to the complex number? Well, this is difficult with the regular representation, the a plus b times I, but I can apply the logarithm here fairly easy. So I can apply the logarithm to my z. So the logarithm of z is so we apply the logarithm to r times e to the power of I times theta. And now we can simplify this with the logarithm. So the logarithm of z is eventually, since it's a logarithm, we can just move this, well, we won't do this yet. So what we do now is we can actually, so we have this product here. So we can say the logarithm of the product is the sum of the logarithms of the components. So the logarithm of r plus the logarithm of e to the power of I times theta. And then we have our logarithm of r, and we have the logarithm of e to the power of something. So this is I times theta. So this was an excursus. We apply the logarithm to a complex number. Now we can come back to our original question, I to the power of I. And what we can do here is we can say we have our I in so the blue one, and we can express our I just in terms of e to the power of ln I. So this one here is just the one we focus. E to the power of ln of something is just that something. So, and we raise all of this to I. Well, let's put this I in green. Now, it turns out we can move this I, the green one, and we can say, well, we have our e to the ln of I times I. So we just move this here. So rather than the power of something, we put up there the product. So e to the power of I times ln of I. So far, this doesn't have to do much with complex numbers because we just use regular algebra rules you're all familiar with. But now comes the interesting part. We want to know what's the logarithm of I. Just down here, we've seen this excursus. We can try to think about this. So remember, I want a geometric representation. So this is the real part, and this is the imaginary part. And what I want to know is, so we have one here, one here. How do I plot my complex number? That is z is just an I. I put it here because what this is, it's 0 plus 1 times I. Now I need to think about this angle, theta. What is that angle? 90 degrees, yes, or pi half. So theta is pi half. Now, this is our interesting part, the ln of I. And remember from before, I'll just write this, what we did in the excursus, I just write it here. So if z was r times e to the power of I times theta, we saw that the ln of z is ln of r plus I times theta. Just what we did down here, step by step. Now, my I up here, this distance here, this r, is just 1. So let's plug all of this in. We have our I from before, and we have our ln of I. So this is the ln of r, and r is 1, so ln of 1 plus, we have this I down here times theta, so plus I times theta, which is pi half. Now I can try to simplify this, which is e to the power of I. ln of 1 is just 0, so it's I times pi half. And just to simplify it, we remove these parentheses, so we have I times I pi squared, so it's e to the power of I squared times pi half. So this is e to the power of minus pi half, since the I squared is minus 1. If you use your calculator for e to the power of minus pi half, this is something like approximately 0.20788. So since we know how to do the logarithm or how to calculate the logarithm of a complex number, we're now able to calculate things like I to the power of I. Did you find this interesting? Did this give you some new insights about complex numbers? If you feel this was something new, something challenging, let us know. It's just some extra practice about complex numbers, but I promised you, those of you who have studied complex numbers before would most likely see something new today. And this turns, we can do other strange stuff. So for example, we can take the ith root of I. Anyone has ever seen something like this before? This actually is much simpler than you could think from what we have just calculated, because we can say this is I to the power of 1 divided by I. We can simplify this further. Remember, before we said if we have something like 1 divided by I, we can extend this. So we have, we do this extension, which is 1 times I divided by I times I. And then this I squared becomes minus 1. So what we get here is I to the power of minus I. The I squared is minus 1. So this is I to the power of minus I, which then becomes 1 divided by I to the power of I. And I to the power of I, we have just calculated before. So this is 1 divided by e to the power of minus pi half, which is something like 4.81048 and so forth. So this one here in red is simple because we have just done it before, step by step. But as you can see, even calculating the ith root of I is something doable. If you feel this was something new and surprisingly simple, let us know with some reaction. I've seen other very strange stuff in YouTube videos by this Iranian guy whose name I forgot, but if I come across it, I'll share it. He even proposes strange stuff like to take the root of a matrix or a matrix root of a matrix. So I've seen all of these videos on the internet, often watch them when I'm in hotels. And yeah, it turns out you can do very interesting stuff in maths, like the square root of a matrix or the matrix root of a matrix. It's all possible. But here we are working on complex numbers today. So I hope you got a good revision of complex numbers, plus you've seen some new stuff, because we will need complex numbers throughout this course. And you know now how to calculate I to the power of I, or the ith root of I. Everything I have shown you is also here in the slides where it's well typed, and I hope I don't have any mistakes in my live calculations, but you can always find this in here in case you wish, as well as the ith root of I. Now we've done the complex numbers, and what we're doing next is vector spaces, and we will have a quick revision of vector spaces. And what we need to know is if you have something like R, the real numbers to the power of n, this denotes the Cartesian product of R with itself, up and so forth. And so R to the power of 3 would be the Cartesian product of R, R, and R. And we would use this, for example, to express vectors, because vectors, they have n elements, and so far you have seen vectors with real numbers. And we will now briefly look into the addition of vectors, the length of vector. We will look at scalar multiplications. We will see geometric representations. We've actually done the length and the geometric representation just before with our complex numbers. We'll briefly talk about vector spaces for which we need a basis and a dimension. And then we will see matrices. And in matrices, it's R to the power of m times n. So we have m many rows and n many columns, and we can add, multiply, transpose, and so forth. We will do this very quickly as a revision for the real numbers. And once we're done with that, we will actually switch to complex numbers. Do you all feel okay with vector spaces on real numbers? Maybe let us know here with some reaction. You all should have learned vector spaces at some point in your Maths 1 or Maths 2. And there will be just a very, very quick overview about the real numbers, because it's really a revision. But after we've done this, we will do the same concepts on complex numbers. So, for example, vectors, we can have a vector v1, which are the elements 2, 5, 2, 5, and 4. And we have v2, which are the entries 1, 0, and -2. And I want to know from you what's v1 plus v2. If you have a solution, what the result would be, send it to the chat. What we do is these vectors need to be need to have the same number of elements, and we just sum them up element-wise. So this is 2 plus 1 is 3, 5 plus 0 is 5, and 4 minus 2 is 2. So fairly easy. Then we can also have scalar multiplications, for example, 3 times vi. What I do is I multiply 3 with each of the entries. Maybe you can just send us the result. What's 3 times vi? So it's 2 times 3, which is 6. 5 times 3 is 15, and 4 times 3 is 12. So that's fairly easy. And then there are lots of other concepts when it comes to, for example, geometric representations. For now, we'll constrain this to some vector b3, which is 3, 5. So this is x1, this is x2. Can try to plot v3 in here, in this plane. So 3 and 5. So this would be our vector v3. And you still remember how to calculate its length, because we've just seen this before when we looked at complex numbers. And obviously, this concept can be applied to vectors with more entries. Maybe we'll just do this very briefly for revision. Tell us what's the length of vector 2. So we have vector 2 over here, and we'll compare your results. So this would be 1 squared plus 0 squared plus minus 2 squared. So this is just the square root of 5. So we take each entry, we square it, we sum the squares and take the square root of that sum. So it not only works for 2 entries, but for multiple. Then there is another concept, which is a product of 2 vectors. So v1 times v2. For example, we would just calculate the scalar product. Maybe you can tell us what's the scalar product of v1 and v2. If you should all be familiar with the scalar product. So it's 2 times 1, 2 times 1 plus 5 times 0 plus 4 times minus 2. So it's 2 minus 8, so should be minus 6. So we just element-wise multiply these entries, and then we sum these products and we get one scalar number. So this is the scalar product. There are some other products like the inner product or the dot product. That's essentially what we have just done with the scalar product, but these concepts of products can be a bit more generalized with these terms dot product, or then further with the inner product. But these kind of multiplications is something we will see more often also later, or in a moment when we look at matrices and when we wonder how we can multiply them, which is yet another generalization. Then there is the concept of so-called vector spaces, which is the basis and dimension. I won't be able to provide an in detail revision of these concepts now, because it's just a revision lecture and you have studied these concepts in detail. But a vector space always has some basis. For example, if you have 3 entries, a typical basis would be something like this, and then a vector can be built from this basis. But you can have a different basis. You can convert from one basis to another, and it's something you have probably studied in detail in your Math 1, Math 2, and the concept of dimension also is a consequence from this. Then, very briefly, we will still look at matrices. And when we look at matrices, we can say we can have M1, which is a matrix, something like entries 2, 0, 4, 1, and M2 is 1, -1, 2, and 4. And I want to know from you what's the result of M1 and M2. So we add M1 and M2, and what we do is we just add those element-wise. I'll wait for you to calculate the sum of these two matrices. So it's again element-wise, so 2 plus 1 is 3, 0 and -1 is -1, 4 and 2 is 6, and 1 and 4 is 5. So we can just sum these two matrices. We can also multiply matrices. So in order to add the matrices, the number of rows and columns need to be the same. So otherwise we cannot add them. And we can also multiply matrices. So multiplication. And for this, we multiply an M times N matrix with an N times P matrix. So we will look at that now. We can just do this. We just assume M, N, and P are the same. We could just multiply M1 with M2. And there are different tricks how to do this. The way I personally like to do this, so 2, 0, 4, 1. So this was my M1. I personally like this notation here to multiply two matrices of 1, -1, 2, and 4. Have you seen this notation here before, to put the two matrices like this in order to calculate the product? Maybe just thumbs up, thumbs down if you're familiar with this notation here. Many have not seen it, but I personally like it a lot to calculate the product of two matrices, because what I'm doing here is I have this column and this row, and what I'm doing is I'm just taking the product of this row and this column. So what I'm doing is I'm multiplying them element-wise and I sum them up. So 2 times 1 plus 0 times 2, so it's just 2. This is the result here. Then I can also do this for the next row. So it's 4 times 1 plus 1 times 2. This is 6. And you can just continue and try to calculate the next two entries of our result matrix. We have one answer already, but I'll just wait a little bit and see if more of you have the answer. So we can see 2 times -1 plus 4 times 0. So this is -2. And then 4 times -1 plus 4 times 1 is 0. So this would be the result of multiplying these two matrices. And I personally like this notation here a lot, that we put in the lower left the first matrix, and in the upper right the other matrix, and then it's fairly easy to see which rows and columns we need to multiply. Do you personally find this scheme helpful, like this, to calculate the multiplication? Maybe just let us know if this is something you find helpful or not. I personally like the scheme a lot and use it all the time. But every year I see some students who had not come across this before. But if you don't like it, that's fine too. It's personal preference. There are a few more matrix concepts we briefly need to look at, which is the transpose. So say we have a matrix which is 2, 3, 4, 5, 6, 7. And I want to know from you, what's the transpose? Anyone remembers this concept? Maybe if you remember the concept, let us know. If you don't remember it, also let us know. So everyone remembers it, so I don't need to explain it in detail, but you can quickly tell us in the chat what the transpose of M would be. Already telling you this, M has 3 rows and 2 columns, and the answer will have 2 rows and 3 columns. So this is 2, 4, 6, and 3, 5, 7. So just turn rows into columns and columns into rows. And then there is another concept, the inversion. If I have a matrix and I multiply it with its inverse, what is the answer, or what's the result when I multiply a matrix with its inversion? Do you remember this? And that's correct. It's the identity matrix. I'm not showing now in detail how to calculate the inverse. It's something you have learned in Math 1 or Math 2. So it was just a quick revision. And the identity matrix, say I2, so the 2 times 2 identity matrix, it's a 1 here and a 1 there. So in the diagonal, we have 1s and the other elements are 0. We can also have the 3 times 3 identity matrix, which is just 1s here, and then the other entries are 0. Then there's also the concept of a determinant, but don't think we need a determinant much in this course, so I'll skip it. The last concept that is quite important is eigenvalues and eigenvectors. For whom of you does eigenvalues and eigenvectors ring a bell? Let us know with some signal. For most it does, but for some it does not, and that's absolutely fine. So I'll quickly show you the intuition of what's the idea behind eigenvalues and eigenvectors. Imagine I have a matrix, and the matrix is, for example, 4, -1, 2, and 1. If I take this matrix and I multiply it with 1, 1, what's the result? We have just revised how to multiply two matrices. Maybe let us know what the result would be when I multiply this matrix and this vector from the right. We got an answer already. It's 3, 3. And 3, 3, we can say, is 3 times 1, 1. So I have multiplied 1, 1 with this matrix here, and I got a multiple of 1, 1. Technically speaking, this is a so-called eigenvector of the matrix, because an eigenvector, not every matrix has eigenvectors, but some do. And if you have an eigenvector and you multiply it with the matrix, you get a multiple of the eigenvector. And this multiple here, this would be the eigen or the corresponding eigenvalue. And you can also, this multiple is either positive or negative. And from a geometric representation, so you wonder what is this actually useful for, these eigenvalues and eigenvectors. If you have an eigenvector of a matrix, so this is our eigenvector, say this is, for example, 1, 1, and I multiply it with the matrix, I get a new vector. And in our case, this would be, for example, the blue one here would be 3, 3. So this vector 1, 1 becomes longer or shorter, because this factor here could also be, say, a half or a third. But we just change the length of the vector, not its direction. What can happen is if the eigenvalue is negative, so if it was, say, -3, we would just flip it. So this would be then, if the eigenvalue is -3, but we just invert the direction, but we don't really change the angle or anything like this. So we just flip it to the opposite direction. When you study an introduction to linear algebra, you learn about the eigenvalue and eigenvectors. Have you seen any applications of this kind of stuff? If you have, maybe send this to the chat and I'll wait for you. If you have never seen applications of eigenvalues or eigenvectors, then maybe just send a negative reaction and I'll just wait a bit in the chat and see if anyone has seen applications of this kind of stuff. So someone has seen applications in robotics. Yes, they exist. I'll see if anyone else has seen applications of all of this. Someone has seen in robotics. It turns out there are some applications, for example, so someone says when you have a state space, then the eigenvalue is the root of the characteristic equations or something from control systems. Someone writes, okay. One application, someone else says in motion control, in automotive. And now one student wrote the one I wanted to refer to, PCA, the so-called principal component analysis, PCA. And PCA allows you to map your data to a different basis, and this can be used to reduce your data or the dimensionality of your data. So this can help to, you have some loss potentially then, but it allows you, you have a high dimensional data set and you map it to a lower dimension. And PCA is typically done using the eigenvalues or eigenvectors In practice, many people use this so-called SVD for PCA, which is the singular value decomposition. This can also be used for PCA, which is more or less just a generalization of this eigenvalues and eigenvector approach. But SVD is a more advanced concept from linear algebra, so we don't need this here in this revision. Someone also has come across eigenvalues, eigenvectors for PID controllers and closed loop systems in control engineering. Okay. And now the very last concept from linear algebra is the trace. Anyone heard about the trace before? Send us again some reactions here in the chat, whether this concept rings a bell or not. And since one person knows it, maybe you want to tell us what is the trace. So for example, trace of this matrix here, which is 1, 0, 2, 4, 5, 6, 8, 9, 1. What is the trace of this? The trace, that is not in the chat, is a sum of the elements in the diagonal. So the trace would be 1 plus 5 plus 1. So that would be 7. Because we may come across this term trace at some point, or you come across it in the book. So you know it's the sum of the elements in the diagonal. So this was just a very quick revision of vector spaces. And now we will actually start with something quite exciting. Because we have now done all of this for real numbers. And it turns out you can do all of this for complex numbers as well. All the stuff we have seen, addition, length, scalar multiplication, these products, all of that can be done as well if we don't put real numbers into our linear algebra structures, but we can put in complex numbers. The concept of vector spaces, basis, dimension becomes a bit more complex, but I can also have matrices that I add, that I multiply, that I transpose, and do the calculated determinant, the inverse, the trace. This can all be done for complex numbers as well. And most of this, especially these things here, they don't really change. We just use complex numbers, but not real numbers. What gets a bit more tricky are eigenvalues and eigenvectors on matrices that store complex numbers, but we don't need to study this in detail. We will do some examples very soon. And then once we have done these examples, it will turn out there are also some new concepts. Because when I put complex numbers in my matrices, there are new concepts like the conjugate matrix, the adjoint matrix, and unitary matrices. And after we have done all of this, we will also look at one extra concept, which are tensor products. These tensor products, they are not constrained to complex numbers. We can also do them using the real numbers. And this is a concept we will introduce as well, because we will need this later when we describe more complex quantum systems. If we have multiple quantum systems and we want to assemble them into one large joint or one assembled quantum system. And for this, we will need a concept called the tensor product. And we will now look at concrete examples with complex numbers in here and see that it actually doesn't get that difficult. Now we will plug in concrete complex numbers. Imagine we have a vector, so like complex vector spaces, or simply complex linear algebra. So we have V1, which is 5 minus 2i, 1 plus I, and V2 is, say, I and 5 plus 2i. I want to know from you, I have these two vectors and I want to add V1 and V2. What's the result? If you have suggestions, send them to the chat anytime. So this is 5 minus 2i plus I. So it's 5 minus I. And then we have 1 plus I plus 5 plus 2i. So it's 6 plus 3i, because we just add two complex numbers. We can also do the scalar product and all of this. Obviously, we can do a scalar multiplication. Say I have a complex number which is 2 plus I, and I want to multiply this with V1. So 2 plus I, and we multiply this element-wise with V1. So it's 5 minus 2i and 1 plus I. And it's now your task to do this scalar multiplication and tell us what you think the two entries, or maybe let's start with the first entry. So multiply this and that, and then this and that for the second entry. If you have a suggestion for the first entry, let us know. We already got a first suggestion. So I'll do it step by step. So it's 2 times 5 minus 2 times 2i. Then I have plus 5i and minus 2i squared. Oh, I got it all right. So we'll continue this for the first element. So this is 10, and the i's will be 1i, so plus I, and this will be 10. And here, minus 2i squared will be plus 2. So we will have 2 plus 10, so it's 12 plus I. The solution in the chat is correct. And you can continue this for the next entry. So 2 plus I times 1 plus I. So we have, I'll do this in parallel while you try. So it's 2 times 1 plus 2 times I plus I plus I squared. So this will be, we have 2 and we have the 3 i's, so plus 3i, and we have the 2 and I squared is minus 1, so it's 2 minus 1, so it's 1 plus 3i. We can obviously do this also later if we want to multiply matrices and so forth. In add matrices, it's just the same concept over and over again. So same for a transpose. The only thing we can test now together, because the concepts aren't really different. All we do is we plug in complex numbers, but I'll look for one example now. Say we have a vector v2 and has multiple entries, so 4 plus 3i, and it's 6 minus 4i, and say I. So this vector has 3 entries, which are complex, and I want to know what's the length of this vector or the norm of the vectors. Also a term used, norm or length. I want to know from you what's the length of this vector. I will already tell you the intermediary steps. So we have 3 complex numbers in here. So this will be the square root of the length or modulus of the first complex number, which is 4. So this is the modulus of the first complex number, and modulus squared, because the length of that, if you see this complex number as a vector squared, then plus 6 minus 4i modulus squared plus the modulus of I squared. So this is an intermediary step, and you can think about what's the length of this, or the norm of this vector now. Do you all feel okay with this? Because I didn't see any answer in the chat yet. If you feel okay with this and you're doing progress, maybe send some green reaction. If you're lost, maybe send a red one, and then I just see how it's going. But there were a few very active students before, so it would be cool to compare your results. So we got a future. If you look at this, so 4 plus 3i, and you want the modulus of that complex number, you would have 4 squared plus 3 squared, so 16 plus 9 is 25, but you take the square root, and then you would have the modulus here, so square root of 25, which is 5. And we take this and we square it. So this one here, as we said, square root of 25, which is 5. But then we take this and square it plus this one here is 6 squared, so 36 plus 16 from the 4 squared. So it's 52. We just saw a solution, but someone deleted it. So don't be shy to put it here, because I know this is not easy. And we're all likely to do something wrong at some point. So I hope I didn't do it wrong, but please, you can also try your solution and see if you get something similar. That's obviously like this. So we have to, well, not very happy with my pen at this place here. Just wait a second. So square root of 87, and that's correct. And the square root of 87 is approximately, if you're curious, 8.832. Because we have the 25 here, 52, 25 plus 52 is 77 plus the 1. So it's the square root of 78. We got one answer that is correct. Do you all feel okay with this example now? I know it takes a little bit to get comfortable with this because we take the square root of some modulus of complex numbers, we square them again. But this is a good practice because we will need this in one of the next chapters quite a lot. And there will be more examples. So in case this first example was a bit overwhelming, there'll be many more examples of that sort throughout the course. Now, we could still try to multiply and transpose and so forth matrices that have complex entries, but we will now look into new concepts in complex vector spaces. And one example that we will see now is the conjugate matrix. Remember, we looked into conjugates of complex numbers earlier today. And if you remember, the conjugate was, we just changed the sign of the imaginary part. Now, there's a new concept in complex vector spaces, the conjugate matrix. And this one is often denoted as A bar. Sometimes it's denoted as A star in the literature, because the star is sometimes used also to describe the conjugate of a complex number. Now, if I have a 2 times 2 matrix, just as one example, which has entries A, B, C, and D, and I want to know what's the conjugate matrix of A, so A bar, this would be, and elements A, B, C, and D are complex numbers. This would be A bar, B bar, C bar, and D bar. So all I'm doing is I take the conjugate of every entry. Let's look at a concrete example. So 6 minus 3i is the first entry. The next entry is 2. The third entry is 9i. And the last entry is minus 2 plus 4i. And I want to know from you, what's the conjugate matrix? Should be fairly easy since you know conjugates of complex numbers. Send your solutions to the chat. Well, the first entry is 6 plus 3i, because minus 3i becomes plus 3i. The second entry doesn't change because it only has a real part. The third entry only has an imaginary part, 9i, which becomes not minus 9i. The last one is minus 2 minus 4i. So fairly straightforward. This is a new concept, the conjugate matrix. And we will extend this now with a few more steps, and then later today, we will see a very important concept in complex linear algebra, which we will need all the time in quantum computing. And building on top of this conjugate matrix, we will now see the so-called adjoint matrix. And the adjoint matrix is often written as A, then you put this sign here. It's not a plus, it's a dagger. So we pronounce this as A dagger. It's not a plus because it's more like a cross. So it's an A, or in the visualization, a dagger. So A dagger. And this is a new concept as well, this adjoint matrix. And I'll show you how it's defined. Very importantly, this concept here of the conjugate matrix is not just constrained to 2 times 2 matrices, obviously to other dimensions as well. And this adjoint matrix, again, has entries, complex entries, A, B, C, and D. And the A dagger, so the adjoint, is very similar to the conjugate matrix because we have an A conjugate and a D conjugate. But what we see is, I'm putting this in blue, the adjoint matrix is a bit different to the conjugate matrix. I take the conjugate of every entry, but I also transpose the conjugate matrix. So the adjoint matrix is the conjugate matrix plus I transpose it. That's why B and C get flipped here. And if we go back to our example matrix from before, which we said A is 6 minus 3i, 2, 9i, minus 2 plus 4i, I want you to compute A dagger, so the adjoint matrix of A, which is actually straightforward if you have done the conjugate matrix before. And I'll give you a short moment to send your response. So we have already answers in here. So it's 6 plus 3i, like in the conjugate matrix. And this entry down here, the last entry, will be as in the conjugate matrix, so minus 2 minus 4i. But then I have the 2 and the 9i. So the 2 comes down here because I have the transpose, and the 9i goes up here as a minus 9i. That's just one extra step than the adjoint, than the conjugate matrix, because the adjoint is just one extra step. And now we introduce a concept. I've informed you already that this concept would come, which is super important in quantum computing. These are so-called unitary matrices. So what is a unitary matrix? U is a matrix, and it is unitary if the following condition holds true, that U dagger times U is the same as U times U dagger, and that product must be the identity matrix. Identity matrix is something we revised before. As you remember, the identity matrix is all zero except the first diagonal, which is one, which are only ones. So U dagger times U is the same as U times U dagger, and that must be the identity matrix. And these unitary matrices, we will see in a few weeks, are are key to quantum computing, because in our digital computers that we use nowadays, we have fundamental operations which are not and or, the fundamental logic operations or binary logic operations. And so, as we have in a traditional computer these fundamental operations not and or, we will have fundamental operations in a quantum computer which are different. There are various fundamental operations, but they are quantum mechanic, and we will see that these fundamental operations can be expressed as so-called unitary matrices. And this allows us to do quantum computing. And it comes with some other benefits that we will see in a few weeks, but trust me for now that unitary matrices are super important for quantum computing. And in order to understand the unitary matrices, we need to know this dagger concept, so the adjoint matrix, and for adjoint matrices, we need the conjugate matrix. Now, we will look at a very simple unitary matrix. Do you have a suggestion? What's the simplest unitary matrix possible? I'll give you a moment to think about the simplest unitary matrix possible, and you can send it to the chat. If we got it already, it's the identity matrix. For example, let's look at the 2 times 2 identity matrix. So I2, just as an example, is 1, 1. And if I take its dagger, so I2 dagger, this is still 1, 0, 0, 1. Because these entries in here, they only have a real component, no imaginary component. So these entries don't change, and through the transpose, they don't change either. So here we can see very simple, if I multiply the unitary matrix if I multiply the identity matrix with itself, I get an identity matrix. And if I take the adjoint of the identity, it just stays. So this is just the same. And this is just the identity. Here I've just put this for 2 times 2, but we could also just delete that because it applies in general, whether it's 2, 3, or 4 rows or columns or whatever. So this is the simplest unitary matrix we can think about. It's just the identity matrix itself. It turns out there are others. And one that we will see very, very often in this course when we look into quantum computing is the so-called Hadamard matrix. And the Hadamard matrix is a basis operation in a quantum computer. It actually creates a so-called superposition, but we will study all of that in the next few weeks. For now, you don't need to understand what the Hadamard matrix does. For now, it's just one matrix that we work with. What it's useful for in quantum mechanics is something we will see in a few weeks. We often denote this as H, and what the one simple way, or one way we could write it, is something like this. The first entry is 1 divided by the square root of 2. The second entry is 1 divided by the square root of 2. And the next one is 1 divided by the square root of 2. And the last one is 1 divided, minus 1 divided by the square root of 2. This Hadamard matrix turns out to be super helpful in quantum computing, and we will study it in a few weeks, and we will see why it actually looks exactly like this. But what doesn't look nice are all these fractions, so makes it quite unhandy. And in fact, the way we would always look at is we just move this factor 1 divided by square root of 2 out. So we have a 1, 1, 1, minus 1, because this is just a scalar factor for all the entries. You're maybe wondering, why is it square root of 2, not square root of 3? We will see this when we study quantum mechanics, because this 1 divided by the square root of 2 is a normalizer, so we're actually dealing with quantum mechanical states. But all of this is something we will study. Now I'm asking you, what is the adjoint of the Hadamard matrix? So I have my Hadamard matrix, and what is its adjoint? So H dagger. It's still the Hadamard matrix, and so it's we have this normalizer here, and it's still 1, 1, 1, minus 1. And it turns out, if you multiply H times H dagger, it's the same as H dagger times H, and this will be simply 1, 0, 0, 1, which is the 2 times 2 identity matrix. This is something you can try out at home as your homework, because you have the H dagger and you have H, and you should multiply the one with the other and then just the other way around, because we need to see that it's not just H times H dagger, but H dagger times H. And since the matrix multiplication is not commutative, we have to try both. So you have to do these 2 multiplications. Well, here actually you just need to do it once, since we see H dagger is just H. So try out H times H dagger times H, or just H with itself, since H dagger is the same as H. And check whether you get this result 1, 0, 0, 1. Don't forget these normalizers. Don't just multiply the matrices, but also this scalar factor, and you will see you get the identity matrix. And in a few weeks' time, we will discuss in detail what the Hadamard matrix does and why it's so important to quantum computing. We will see many more unitary matrices, and we will see more complex ones, and the ones we see, for them, actually U and U dagger will be different. It's just here for the Hadamard matrix that these two, that H and H dagger are the same, but we will see more advanced, more complex unitary matrices for which U and U dagger are different, yet if you multiply them, we'll get the identity matrix. Now, I'll switch back to my slides. What we discussed in the slides was this one here, our agenda. Meanwhile, we have discussed the conjugate, the adjoint, and unitary. What you see here is in the slides. It's well formatted. I had shown you this on the iPad, and the examples as well as what a unitary matrix is. For today, there is another concept that I already told you before. It's the tensor product. And the tensor product is denoted by this symbol here. Very importantly, this is not an XOR. An XOR is often written when you rotate this a little bit, so that the cross is just rotated by 45 degrees. This is not an XOR, so you please write it this way, the way I put it here in the slides. It's the tensor product. And the tensor product of two vector spaces, V and W, which have to be over the same field, will lead to a new vector space that we can think as the space of all tensors that can be built from vectors from its spaces that it's made of. And probably you're wondering, what is that thing useful for and how does it work? I will show you this now. I have a very generic definition here of the tensor product. For example, we have 2 times 2 matrices, but it doesn't need to be 2 times 2 matrices. And these matrices could also have different sizes. But I have my entries A11, A12, A21, and A22. And I want to have a tensor product with this matrix here, which is B11, B12, B21, and B22. And the tensor product, so I have a 2 times 2 with a 2 times 2 matrix. The tensor product will be a 4 times 4 matrix, and it will be what we get are products. So you see the first 4 elements up here, simplified this here, we take our A11, which comes from the first matrix, and I multiply it with every entry of the second matrix. So A11 times B11, A times 1 times B12, which would be down here, A11 times B21, which is here, and A11 times B22. This is the first block of the matrix, and I do this for all the other elements in A. For example, for A22, I multiply A22 again with each entry of the second matrix. And then I have these 4 entries here in the lower right. This is a very important concept because next week, when we look into systems, so next week we start with deterministic systems, then we build probabilistic systems, then quantum systems. So step by step, we're now moving to quantum. In quantum computing, we will have so-called systems. And when I want to assemble systems, so put systems together, then I can build them very easily by calculating this tensor product. And just to get some practice with the tensor product, we'll do one exercise and then we are all on the same page. So I will screen share. So what we can, just thinking about a quick example that isn't too complex that we can think about. We can take 2 vectors just to keep it simple. So we have the tensor product, and we have our first vector, which is 3, 4, 7. And we have the tensor product with -1 and 2. And I want to know from you, what's the answer when I have the tensor product of these 2 vectors? So it's not matrices here, it's just vectors, but then we also don't need to write out that many numbers. So I'll build this now. step by step. So we have the 3 here, then 4 here, and the 7. So this was the first step. Any of you, like anyone wants to tell me the first entry of the result? Because the result is a vector. So if you have a suggestion for the first entry, it's correct. It's 3 times -1, so it's -3. What would be the next entry? 3 times 2 is 6. Next entry, -4, and then 8, -7, and 14. Since it's a tensor product, we've generically defined it with matrices, with a vector. We just have one column, but that's fine. And next week, you will see what this tensor product is useful for. So when we have systems that we put together. And speaking about next week, we'll make it there very quickly now. So you're obviously encouraged to read chapter 2 of the Janowski and Manucci book. Today, we've looked into various concepts around complex numbers, complex or linear algebra, then complex linear algebra. If you want more practice or read some concepts in greater detail, especially if maybe you need a bigger revision with, for example, complex numbers, please check chapter 2 of the book. And next week, we will look into systems. And next week, we start with deterministic systems, for which we use vectors and matrices. We use also, for example, transposes. And we can see how a so-called deterministic system can evolve. We'll use some visualization for this. So our system has a state, and we'll be using vectors to describe the state and matrices for the evolution. After that, we will use probabilistic systems for which we use probabilities. Next, we use quantum systems for which we don't use real numbers, but rather we will use complex numbers. So we plug complex numbers into our states and matrices, and then we use the tensor product to assemble systems. And like this, next week we will get exposed a bit to quantum systems and assembling such systems. And once we have done this, we will have probably in 2 weeks' time, we look deeper into quantum mechanics. And once we have done this, we can start actually doing quantum computing. So it takes us a little bit to make it there. But in essence, today we've revised complex numbers. There was some new stuff around complex numbers for most of you as well. And we saw complex vector spaces. And everything we're doing as of now in this course is essentially we use complex numbers and linear algebra to build things. Next week, we start with these systems, first deterministic systems, then probabilistic ones, then quantum ones. But the theory is not getting much more difficult than what we have seen now. We will obviously understand what unitary matrices are useful for and why they are so important. But now you know the definition of unitary matrices. And once we have built this and digged a bit deeper into quantum theory, but all the quantum theory we look at, it can all be described by the mechanisms we have established today. Then in a few weeks' time, we can see how we can use these vectors and matrices for computations, and later how to build quantum algorithms from them, and see how we can program real quantum computers. That's why, since everything we're doing in this course will be based on these foundations today, please make sure you revise everything. And if you have any questions, let me know. Make sure you're familiar with the calculations, because next week when we build our systems, we need this. And from there, we dig deeper into quantum mechanics. Are there any questions so far? Um, if you have a question, maybe just raise your hand so I can wait for you. Since you all seem to be okay, we're finishing a bit earlier today, so you still have time for revision. And next week, we'll move on with systems where we use all of this theory. Thanks for all your contributions in the chat, and I look forward to seeing you next week in a lecture. Have a good weekend. Take care. Bye bye.